BioCAPT operates as a classical pipeline composed of 53 distinct cognitive modules. Layers like the neuromorphic event-driven activation, or NETA, interlock to process information in a continuous, dense digital network. Porting that level of architectural complexity onto current-generation quantum hardware introduces severe physical constraints. Processors like IBM's Marrakesh and the Origin Q systems offer exactly 156 qubits, and they are inherently noisy environments. Deeply complex AI algorithms require long sequences of operations, known as circuit depth. On bare quantum hardware, as circuit depth increases, the quantum states lose their coherence before the calculation finishes, causing the data to dissolve into random noise. Because of this physical limitation, BioCAPT relies on a strict internal policy of evidence-governed cognition. This means the system rejects theoretical claims of quantum acceleration or speedup until they are proven with local, empirical data. Building a functional quantum AI requires prioritizing execution stability over speculative processing speeds. If the algorithms cannot survive the physical hardware, theoretical acceleration is irrelevant. To solve the hardware translation problem, the architecture deploys two specific mathematical mechanisms: the variational quantum eigensolver, or VQE, and quantum error correction, or QEC. This diagram illustrates the first mechanism. VQE acts as a continuous translation layer. It takes the classical Python runtime instructions on the left and converts them into parameterized quantum states on the right. Once that translation occurs, QEC provides the physical stability layer. It wraps the quantum circuit in structural error correction logic, preventing the quantum states from collapsing while the calculation is running. Running both of these mechanisms simultaneously requires significant classical computing power. The system burns substantial overhead, simply managing the error correction and translating the variables back and forth to keep the baseline quantum functionality alive. By treating quantum computing as a hardware environment that must be actively managed and corrected, the BioCAPT framework moves quantum AI out of abstract mathematical theory and into a rigid engineering discipline. To understand how this works in practice, we can isolate a single cognitive module from the pipeline, such as the allostasis orchestrator, or LOQ. The classical logic of this module is translated into a hardware-efficient ansatz, a mathematical template that configures the quantum gates to represent the module's parameters. This chart tracks the hybrid classical quantum loop driving the module. In the first phase, the quantum state executes on the hardware and outputs a specific numeric result known as an expectation value. That expectation value is immediately handed off to the classical Qiskit 2.x sampler Z2 layer, bridging the physical hardware back to the local desktop environment. The local Python 3.14 runtime takes that value and runs an optimization phase. It analyzes the result and calculates the required parameter updates needed to improve the module's cognitive logic. Those updated parameters are then fed in a feedback loop directly back to the QPU, completing the cycle and resetting the hardware for the next iteration. This specific wiring has been empirically validated. There are currently 3 standalone VQE applications executing successfully on the system using this exact loop. Without this continuous hybrid loop, complex reasoning models would fail immediately on noisy processors. By offloading the optimization math to the classical desktop, the quantum hardware is only tasked with what it does best: executing the parameterized state. The 156-qubit processors in use today are characterized by high error rates. Environmental noise, minor fluctuations in temperature or electromagnetic fields, constantly threatens the integrity of the qubits. If a single uncorrected bit flip error occurs, it corrupts the calculation. Within a framework of 53 interlocking modules, that single error will propagate rapidly across the data streams, collapsing the entire cognitive pipeline into noise. Abstract logical AI states cannot exist in this environment alone. They require redundant physical qubit backing to maintain their cognitive coherence long enough to return an accurate result. This diagram shows the specific quantum error correction protocol applied across the BioCAPT framework, the 3-qubit bit flip code. It takes one logical unit of data and splits that logic across 3 parallel physical qubits. An entanglement process links the states of these 3 physical qubits together, ensuring they operate as a unified system. If a simulated environmental noise event strikes the hardware and corrupts the middle qubit, it flips its state from 0 to 1. The system uses a parity measurement technique to detect this anomaly without directly measuring the data, which would instantly collapse the quantum state. Because the top and bottom qubits still hold the correct value, the algorithm executes a reversion, correcting the middle error based on a simple 2-to-1 majority consensus. Applying this specific redundancy protocol individually across all 53 modules is computationally expensive and requires a massive footprint of physical hardware. But that mathematical redundancy is what guarantees the algorithmic stability of the system. It ensures the data is clean before any true cognitive processing is allowed to fire. Because of these rigorous demands, the architecture is governed by an evidence firewall, a validation pipeline that automatically blocks unproven claims from being integrated into the main system. The firewall dictates that all 53 modules must individually pass Qiskit transpilation checks, ensuring their logic can physically map to the quantum gates. It also enforces strict credentialing. Explicit approval gates are mandated before any job is allowed to leave the simulator and execute on actual hardware. The results of this rigorous validation are logged in the execution ledger. In May 2026, the framework verified execution on both the IBM Marrakesh and Origin Q hardware. The system recorded exactly 50 completed QPU jobs, returning 50 matching payload bundles containing the hardware execution data. Alongside the hardware runs, the simulator smoke tests executed and passed 12 out of 12 required behavioral invariants, confirming that the logic holds under testing. Achieving a 100% transpile and hardware execution rate is the mandatory prerequisite for the project. Achieving 100% transpile and hardware execution is the mandatory prerequisite. No future expansion occurs until existing modules prove they can run. This benchmark compares a classical baseline against quantum-inspired execution on a 10,000-item list. The classical architecture completed it in about 0.05 milliseconds. The Grover-shaped quantum heuristic took 91 milliseconds. The massive overhead required to translate the states, run the error correction, and manage the hybrid feedback loop makes quantum-inspired consensus demonstrably slower in these measured cases. This data enforces the strict BioCAPT protocol, prohibiting any claims of quantum acceleration. Until detailed workload maps prove a net new speed advantage, the system assumes classical processing is faster. Proving architectural fidelity and stability is more important to the engineering roadmap right now. Speed is irrelevant if the cognitive modules cannot successfully execute on the physical processors. By locking in the QEC integration, the system stabilizes the architecture's logical qubits against environmental noise. By verifying the VQE wiring, the modules actively learn and optimize across a hardware-efficient ansatz. Next is continuous A/B performance benchmarking against classical equivalents. Solving quantum porting today builds the fault-tolerant groundwork for a cognitive architecture governed entirely by evidence.